Gaze+RST, integrating gaze and multitouch for remote, rotate, scale, transform tasks.
Excellent, thank you. So thanks for all coming along. I guess you're all sat here waiting for SI, so I'll try not to be too long. So today I'm going to present some of the work that one of my PhD students has been doing. So Jayson Turner, Jayson with a Y, can't be here today because he's got a job with the BBC. And so I'm going to present this instead. So it's work we've been doing with Andreas and Hans Gellersen, looking at how we can integrate the gaze modality with multi-touch on a mobile device. And how do we use that in order to do remote, rotate, scale, and translate tasks. So just so you have a bit of an idea of what I'm talking about, the colors look pretty rubbish, so you probably can't even see Jayson on the far right there. But what he is doing is he has a mobile device in his hand, and he's wearing a wearable eye tracker. And he's using that wearable eye tracker to assist his translation, rotation, and scale actions on this remote display. So one of the first questions you're probably asking is, why on earth did we want to study this? Why on earth is this interesting? So gaze tracking is becoming more and more pervasive, and so in the next few years we're going to see more and more work in this area. We're already seeing a lot. And we all have these remote displays kind of everywhere, right? So we all have one sitting in our living room. We have a TV, and we sit in front of that TV with our tablet or our phone. And we also have these in lecture theatres and meeting rooms and every kind of train station. And so we're going to want to be able to interact with these remote displays a bit more easily than we can at the moment. And so just before I get started, there's a couple of terminology things I wanted to clarify. So the terminology I'm going to use in this talk, I'm going to talk about rotation. So this is how you change the orientation of an object on screen. Typically in a touch modality that's used using two fingers, and you do this kind of rotation action. We have scaling, so that's increasing or decreasing the size of an object, and typically on a touch screen that's done using these pinch gestures. And then finally, translation is moving an object from side to side or into a different place. And typically on a touch screen that's done just using your finger. And this is largely where we're looking to replace or to augment our finger interaction with gaze. So how can we use gaze to improve this translation part of these tasks? And so essentially what this paper is about evaluating 4 different gaze and touch approaches to increase the efficiency and to boost the performance of remote manipulation of objects. So the simplest approach to this is to use gaze for pointing, so essentially attach a pointer to your eyes, and touch for this RST, so rotate, scale, translation, manipulation. And so that is largely what the first technique we implemented was. So again, you may or may not be able to work out Jayson on the right. And so in touch translation, the user selects the object by looking at it, and then they use touch input in order to perform all of the translation, rotation, and scaling tasks. In our implementation, we included a control display gain ratio. So if the eyes were a long way from the translation point, then we accelerated the translation to facilitate slightly improved performance. So that was touch translation. And so we sat down and we had to think about how we could better incorporate gaze into this kind of interaction. And so we know largely that gaze aligns with the user's attention. And so if they're trying to move an object to a particular target, then chances are that target is going to be within their gaze at some point. And so we thought about how we can put the gaze into this mechanism in order to boost the user's performance. So we're worried about how much faster can people be using these techniques. And so this brought up a range of questions. So should we do things like, should gaze take full control of translation? So should the object just be tied to your eyes? Or should there be some balance between how much the eyes have control of the object and how much the touch has control of the object? And so in order to try and answer some of these questions, we came up with a couple of other techniques. And so the next technique is called gaze translation. And so the way that works is initially when the user selects the object, it's under their full control. But as the object moves away from its starting position, the object is attached to the eyes and it follows the gaze across the screen. And the user can then perform sort of a slight touch translation to drop that, and then they can perform their rotation scale using the touch input on their mobile phone. And so this is essentially an extended version of something that Stelmark presented at CHI 2013. And then we then thought about how we can better integrate these two modalities. So gaze and touch are kind of these two quite different modalities. And if you think about traditional rotate, scale, and translate actions, they are very integral. So I can change between doing a rotation, a scale, and a translate action without doing any mode switching, and I can even combine those at the same time on a touch device. But we thought about how we might be able to combine gaze and these touch translations in such a fluid way. And so if we think about Jacob's work from 1994, then what he said was that if we want fluid and integral interaction, we need to have an input structure and a perceptual structure that match the task. And so we thought a little bit about what this meant and how we could apply this. And so we thought about things like, well, what is it that gaze can do to assist the multitouch? How can the gaze augment the multitouch? And when we did this, can they achieve concurrent control? So is it that the gaze always happens separately to the multitouch, or can we get these to happen at the same time? And so we designed a couple of other techniques, and the first is called magic translation. And this specifically aims to be more of an integral technique. So in this case, the object is always under the control of touch on the mobile device. However, when the eyes are a sufficient distance from the object, so outside a kind of mask area we have on the screen, that the object is warped to the gaze point, but only when it's initiated by a touch. So it's not locked onto the eyes, it's only warped as a touch is happening. So that's subtly different to the previous one where the object is tied to the eyes. And this is trying to leverage the preemptive nature of gaze. So when we're gazing at a target, then we know that this is probably where the user is going to go. And the final technique we looked at was something called gaze-guided touch translation. And this one basically used the eyes as targeting assistant. And so hopefully you can see on the contrast on the screen, a little white line appears between the gaze point, between the initial object, and where the user is gazing. And essentially what this technique does is the gaze defines the translation path. And so when the user performs a translation, the object will only ever move along that translation path. And the idea with that was to reduce the cognitive load so that the user could focus on the rotation and scale components while that translation was happening. And yes, this is slightly crazy, and you'll see why that is a little bit later. But we hope that this would be a more concurrent technique than the other ones that we were going to try. So like all good HCI researchers, we went and did a comparative study, and we had three main research goals. So the first one was, can gaze offer any performance benefits during these remote rotate, scale, and translate tasks? The second was, do translation distance, rotation, and scale factors affect their performance? And thirdly, do different configuration of gaze and RST affect integrality? So can users perform these tasks where they use the gaze and the multi-touch concurrently? So experimental setup looks something like this. We had 16 participants, and they used all of our four techniques. And the whole idea of the study was to perform these movement, rotation, and scale actions, as you've seen in all the previous videos. The previous videos showed the experimental setup. We had a range of distances, and these are measured in visual angle, a range of rotations, and a range of scale factors that users needed to perform. And they had a training block and then two time blocks during the experiment. So what I'm going to do is I'm going to take you through some of the more interesting results. There's a whole lot more results and a whole lot more statistics in the paper, but do go and read that in your own time if you're interested. I'll try not to bore you with them here. So the first thing we looked at was the performance. So how long did it take people to complete the tasks? And this was measured from the start of the selection until when the object was dropped. And what we saw was that there was no best performer. So there was no kind of difference between the techniques. And then we looked at the difference from when they started the selection to when they entered the target bound. So this was kind of the time to target, which focused on that translation part, going from one side to the other. In this case, we saw that gaze translation was the fastest. So we then had a look at the distance. So does distance to target affect the performance of these different techniques? And kind of as expected, we saw that in general the performance decreased as the distance increased. So this was kind of not unexpected. This has kind of been seen for many, many years. So that validated that result still held. So I guess more interestingly, we then wanted to look at how integral these different techniques were. So could people perform the gaze components and the multi-touch interactions concurrently? And the way that we looked at this was we used Jacob's integrality ratio. And the way that you calculate this is you sample your input stream. So you sample which inputs are being used at a particular time, which slices into 10 millisecond periods. And then in each of those slices, we looked at whether which of the techniques was active during that slice. And so here's an example case where we started off just doing some translation, then some rotation came in, and then some scaling came in as well at the end. And so we then go along and label these different slices. So we can label them city block if we have just one particular input happening, or we can label them as Euclidean if there's multiple inputs happening at the same time. And then to calculate this ratio, then we calculate how many Euclidean blocks did we have over how many city blocks did we have. And so these were the results from this. So what we saw was that none of these integrality ratios were greater than 1. So if you look down that column there, there's sort of 0.6, 0.3, 0.6, 0.58. So this indicated that none of them were more integral than they were separable. So in all of these, there's definitely a component of the two inputs being performed discretely or individually. And we saw that gaze translation was less integral than all the other techniques. So remember, that's the one where the object locks onto the user's eye, and then they can drop it at the other end. We then looked at how much touch translation was being performed on the mobile device or on the touch device. Because this gave us an indication of where that workload was happening. Was it happening on the eyes, or was it happening on the touch display? And what we saw in this case was that the gaze translation and gaze-guided touch translation had more touch input than the magic translation and the touch translation. So you can see that these are the large numbers up here. So touch translation had 483 pixels, and then gaze-guided translation had a mean of 526. And so what that means is that these ones were using a lot more of the touch input than the gaze in order to do this translation. So just a bit of a summary about each of these techniques. So in the touch translation technique, this is a simple solution, and it largely maintains integrality. And so what this is good for is if you have an integral task, but unfortunately most people didn't like this. So it was not the favored technique by people. But what we did see is this control display gain that we added to this technique seemed to work really well. So that if the eyes were a long way from the object, then the translation phase had an acceleration curve applied to it. For the gaze translation, and if you remember, this is the one where the object locks onto the eyes. There was clearly a speed benefit for the object transit part of this interaction. So for moving objects on the screen, then this was clearly fast. But it was largely a separable task. And so the gaze part happened, and then the rotate and scale part happened after the object had moved to the end. They weren't performed concurrently. And so we sort of said that this kind of constrained the use of rotation and scaling. So they weren't performed at the same time as the translation. For the magic translation, so what we saw is that there was no difference here compared to the touch translation. And in fact, in some cases, we saw a slowing of performance with users trying to look at the object as it moved across. So the technique was designed that they would know where the target is, and then the object would catch up because they were looking at the target. But what actually happened was people would want to follow the object to move across the screen, which counteracted the effect that we had designed it for. But this did have greater levels of integrality, so people were performing the rotation and scale components while the gaze component was happening. And finally, for the gaze-guided touch translation, don't use it. It largely wasn't a good design. So we had this mechanic which was meant to help the user by removing inaccuracies in the translation. So the translation path followed the gaze path, but people largely didn't like it, and we ended up with things like overshooting and this kind of thing. So that's not recommended. My time is up. Crumbs. Okay, so overall, here's my conclusion. There are many ways to configure gaze and multitouch, and one of the main things we want people to take away from this is that we shouldn't do this in a naive manner. We should think carefully about how we combine these two modalities. For each of these techniques, we found that for touch translation, this gave full touch control, but it added some of the benefits of gaze selection, and this is really suitable to integral tasks, so tasks that should be performed together. For gaze translation, this is excellent for fast object movement, but should be used when the two modalities should be separated. And for the magic translation, this turned out to be largely integral, but it required very little touch translation. So people didn't use much of the touch screen to perform the translation. And this is quite interesting now that we have more and more small devices, so things like smartwatches where you have very little screen space, or even mobile phones. And another thing we found that warping may be beneficial on long distances. So rather than having to do lots of translation on the mobile device, the gaze and warping can be particularly good for that. Okay, to wrap up. So we saw no performance benefit in these techniques yet, but that's not a reason to stop working on them. Gaze can be combined with these other modalities, and we can make it in such a way that they're integral. But if we only use gaze for translation, that means that it probably won't happen in a concurrent way. So what I want you to take away is that these are kind of promising modalities that can be used in unison, and that we hope that other people are going to kind of take this up and see how far we can really push this and see how we can get some performance benefits out for this remote rotate, scale, and translate. Thanks for listening. Try the other one.
Yeah, try the one.
Robert at Queen's University. Nice work. I think this is these null results are very common in eye tracking, and I've tried my darnest to show that eyes are faster than hands, and they're just typically not. And there's all sorts of reasons for that, but one of the things I found is that when you slave objects to your eyes, you start to overload the input function with an output function. Mm-hmm. So one of the things we noticed in one experiment we did called eye windows, we had targets appear in different random locations on the screen, and actually clicking with the eyes on the target made it more difficult to locate the next target. Mm-hmm. And therefore, we got parallelism in the case where we were using the mouse to click. And that reduced all performance benefits. So to come to the question, have you considered moving the target around? Was the target moving around? Because it seemed to be always in the same spot.
Yes, so it started in different locations. So the videos I showed were just kind of sample videos.
Did you analyze the effect that had, that visual search component, and the parallelism in the pickup? Because if you subtract that from your effects, you might actually find something.
No. So we didn't analyze that effect. So we only analyzed from when they did the initial selection. Right. But that would be interesting if we have the data to go back to that. Yeah. Thanks.
This is really cool. So essentially, what you've done here is you've separated the act of selecting an object from the act of manipulating that object, which is really cool. I'm wondering. So I mean, now that that's separate, there's an infinite number of ways you can imagine manipulating the object, and you've chosen to use touch. Mm-hmm. But you can imagine, maybe you're holding some sort of physical thing and rotating it, and like while you're looking away, maybe that's more natural to sort of fiddle with this physical thing while you're looking at that. Have you considered other ways of manipulating things other than touch, and did you decide on touch, or is that just sort of the first thing you're exploring?
No, that's a really good point, actually. No, so I guess there was a couple of reasons we used touch. So we've used it a lot in our previous work, but we've also, it's something that, everyone carries these things around, right? And so if you're at home in front of your TV, or if you're in a lecture theatre, or if you're in an environment, you have this device to do this manipulation. But it actually would be fascinating to look at how could we design a physical device which would actually make this even more integral and make this even easier. So yeah, really nice point. Thanks.
I had a quick question too. So Mark Hancock, University of Waterloo.
Yeah.
So I also really like this. This is really cool. Did people look at their phone at all, and did that interfere
Yeah, that's an excellent question. I think no, they didn't look at the phone because they knew that in some cases the objects were locked to their eyes, and so this was used purely as an input device, essentially a touchpad, right? So there was nothing on there to see, and they knew that. So yeah, no. Cool, thank you.
Hi, Mike Bennett from Microsoft. Nice piece of work. I'm curious if you gathered any subjective preferences, because using the eye as an output mechanism is often feels quite unnatural, but subjective thoughts?
Yeah, so we did. So people didn't like the kind of the touch translation technique, and I wonder a little bit about whether that was because there wasn't much gaze assistance in that. But yeah, no, this is common in all these gaze experiments, right? We're not used to using our eyes for input, and so there's always this kind of fatiguing sort of tiredness thing. We gave people plenty of breaks to try and reduce that. So, but yeah, no, that's kind of common in these studies. Yeah.
Future work would be lovely to see the subjective kind of reports.
Yeah, excellent. Thanks.
Great questions. Let's thank our speaker.